All right. Hey gang, Justin Zeltzer here from zstatistics.com. Today having a look at the chi-squared test for independence. Now this is one of a couple of chi-squared tests I look at on zstatistics. The chi-squared goodness of fit test is one that I've done as well. And I've also got a video on the chi-squared distribution itself, looking at the history and the derivation. So if either of those interest you, yeah, I'll have them down in the description, or you can hunt them down on zstatistics.com. But if you're interested in the test for independence, you're in the right spot, so let's kick straight into it without further ado. So by way of introduction, let's just recap what chi-squared tests tend to do. We tend to look at a theoretical categorical distribution, some kind of hypothesized distribution, and we compare that with what we get in a sample. So some kind of observed categorical distribution. So in my goodness of fit test video, I gave the simple example where I said there are 3 eye colors, and let's just say that in a given population there's a theory that all 3 eye colors have the same incidence, so the same probability of occurrence. And then we can test that theory by looking at a sample, some kind of observed sample. Now that would be a goodness of fit test. Notably, we're looking at a single categorical variable and comparing an observed distribution to a theoretical one. Now, the test for independence is often given as a separate test, when in my eyes, it's actually the same thing, just for 2 variables. So we might want to have a look at eye colors, but as they relate to, say, sex, for example. So here's male and female, and then again, we've got the 3 eye colors down this way. And we can construct what's called a joint distribution in this yellow box. Of course, you've got your totals around the outside, but this yellow box is called our joint distribution because it's across 2 variables. Now, this is just simply an observed distribution, but we know that when we're dealing with independence, we can construct an expected distribution given that independence. We'll have a look at how to do that when I get into the video proper. But for the moment, just appreciate that this test for independence really is only comparing an observed joint distribution with an expected joint distribution, where our expectations are built up over the theory that the 2 variables are independent. So hopefully you can see that it's just the same thing. We have a theoretical distribution versus an observed distribution in the goodness of fit test. But also in the test for independence, we just have the same thing. It's just that it's a joint distribution across 2 variables, as opposed to just a singular variables distribution. So we're going to dive in now, and we'll be able to see how to calculate this expected distribution. But I thought that would be a nice little introduction, just to get our neurons firing. And now I'm going to dump you straight into the mix here with a test for independence, which will sound a bit like this. 120 people are surveyed for their preferred social media platform. And my question to you is there enough evidence to suggest social media preference is independent of sex? So of course, we're going to need a distribution to assess this with. So here we have a joint distribution. Again, just doing a very simple one that I came up with off the top of my head, males and females. And then we've got Facebook, Instagram, and TikTok, which I still have no idea about, but people a lot younger than me tell me it's quote unquote the shiz. So I figured I'd include it in my sample here. So look, if you've done one of these before, it might be time for you to pause the video and have a go yourself. And let's see if we get the same answer. But if this is your first introduction, let's keep going and see what happens. But the gist is we're trying to assess whether social media preference is independent of sex. So we're looking at the 2 variables here. Here's sex that I've put in yellow up here, male, female. And we're assessing whether that's independent of this variable here, which is social media preference. So keep in mind that this is social media preference, not whether they use that platform or not. So these 120 people are getting surveyed to say, which is your favorite, Facebook, Instagram, or TikTok? So they can only choose one. So you'll remember in my introduction that we have an observed distribution. That's fairly straightforward. They need to give that to us. But how do we find our expected distribution? As in, what is the distribution we would expect if indeed the two variables were independent? Now to find that, we're going to use this formula, which says that the joint probability of A and B is equal to the individual probabilities multiplied together, but only if they're independent. Now, if you've watched a few videos on this channel, you know that I hate equations. I much prefer people using their intuition. So I'm going to prove to you that you don't need this formula, that you have it in your brain already. And I'm going to show you using this little example. So let's play a game. So this is a bit of an aside to our test for independence for the moment, but trust me, it'll be worth it. Let's just say I roll one die and I toss one coin. Now, if I roll a 6 and I flip a head, if both of those two events occur at the same time, you're going to win $100. And my question is, what's your chance of winning the game? Okay, so I need to roll a 6 and flip a head, and then you'll win $100. Now, most people looking at this intuitively will say, yeah, I can see what's going to happen. There's a sixth of a chance of rolling a sixth, half a chance of flipping a head, so I just multiply them together. I get a 12th. There's a 12th of a chance of me winning this game and winning $100. And that's something that doesn't really need formulas. That's all in your head. But the crucial piece of information that you didn't even realize you were using here is that you realized that these events were actually independent of each other. Rolling the dice doesn't actually affect the outcome from the toss of the coin, and vice versa. They're obviously independent of each other, and that's why you could multiply their probabilities so simply. So that's all this formula says. It says, look, if things are independent, you just jam the probabilities together and you'll get this joint probability. Now, why did I spend some time doing that? Well, we're going to be utilizing that fact to create for ourselves these expected frequencies. The joint probabilities in here, these 6 cells, well, they're joint frequencies at the moment, but to find a joint probability, you just multiply the two marginal probabilities together. So let's see if we can use that to form our expected frequencies. Our observed frequency for mail and Facebook was 15. Now the expected frequency, if they're independent, the way to do it is that you take the two marginal values together. So you can see that mail, the total is 50, and for Facebook, the total is 35. You multiply those two together, so 35 times 50, and you divide by the grand total, which is 120. And if you really think about it, what we're sort of doing is taking the probability of someone liking Facebook, which is 35 on 120, and we're multiplying it by the probability of someone being male, which is 50 on 120. Then, of course, we multiply by 120 again to get the frequency as opposed to a probability. You realistically just need to be able to follow this process where you multiply the two marginal values together and divide by the grand total. And then we get the expected joint frequency for mail and Facebook. And it's usually going to be some kind of decimal. It's not going to be a nice round number often. But this tells us that if sex and social media preference were independent, we should have 14.6 males that like Facebook. And we can continue this for the next one. So here's males and Instagram. So we're going to multiply 65 times 50 divided by 120. And here's the formula here. And you'll get 27.1. You can keep going. You can find 8.3 for TikTok and male. And you can do it with females as well. You'll notice we're now multiplying 35 in this case by 70 because that's the total of the female column. And I'm dividing by 120 again. And all the way through, we can find now our expected frequencies. Again, I say expected frequencies if they were independent. All right, so that is really the tough bit done. Now we just need to answer this question. Are they independent? Is social media preference independent of sex? So if we're going to do this in a formal way, we need to set up our null and alternate hypothesis. Our null hypothesis is always that the two variables are independent. So here it says social media preference is independent of sex. And that is going to be our null hypothesis. And our alternate hypothesis is that they're not independent, or in other words, they are dependent. So what this test is going to do is it's going to have a look at the observed frequencies, and we're going to see how close these observed frequencies are to the expected frequencies. And if the observed frequencies are far away from the expected frequencies, we're probably going to reject this null hypothesis. But if the observed frequencies are pretty close to the expected frequencies, we're most likely not going to reject the null hypothesis. So let's find out how this plays out. So our test statistic is a chi-squared statistic, and this is the formula that we use. It's the sum of all of the observed frequencies minus the expected frequencies squared divided by the expected frequency, and we sum them across each of the 6 joint frequencies that we have. Now this calculation is distributed as a chi-squared distribution, but how many degrees of freedom does it have? Now this is the interesting point. In a chi-squared goodness of fit test, the degrees of freedom was k minus 1, the number of categories minus 1. But for a test for independence, the degrees of freedom is the rows minus 1 times the columns minus 1. So we can easily do this because we have, 3 rows and 2 columns, 3 categories for one variable, 2 categories for the other variable. So the calculation's pretty easy. You're just going to get 2 because it's going to be 2 times 1. But why? So why are there only 2 degrees of freedom? Well, let me just delete all of these joint frequencies for the moment. But let's say we had all of these marginal values. So we knew there were 50 males in our sample, we knew there were 70 females, and we also knew the totals of Facebook, Instagram, TikTok, etc. How many pieces of independent information are we going to need to fill in this joint frequency table? Well, let's just say, of course, we're going to need at least one piece of information. Otherwise, these 6 cells could be anything they wanted to be. So I'm going to put in 15 here for mail and Facebook. That's one piece of information. Of course, as soon as we know that 15, we're also going to know that this needs to be 20 here, right? It needs to sum to 35. So 15, it must be 20 to get to 35. So realistically, there's only one piece of independent information that's been provided so far, and it's the 15. Now for the remaining 4 cells, again, we're going to need another piece of information. So let's say we get given this 30. Hopefully you can see where this is going. By being given this 30, we now know this must be 35 to add to 65. And then we're also going to know both values for TikTok because they have to sum to these totals down here. So realistically, there were only 2 unique pieces of information that we needed to fill in this whole table. And that's why there's only 2 degrees of freedom. So anyway, we know then that this distribution has a chi-squared distribution with 2 degrees of freedom. That's why I've got chi-squared with a subscript 2 down here. Now the final clincher is that we must check to make sure all expected frequencies are greater than 5. So we have a look here, and indeed it does look like the expected frequencies are all greater than 5. And so that allows us to say that this statistic will be chi-squared distributed. Why does it need to have all the expected frequencies being greater than 5? Well, that's where that video on the chi-squared distribution might come in handy if you're really keen. Essentially, the reason is, I'll summarize very quickly, but the reason is a chi-squared distribution is derived from a normal distribution. It's actually the square of a normal distribution. And the only reason why these frequencies might exhibit normal distributions is because the sample size is large enough such that the central limit theorem applies. Now, if that's just blown your mind, don't be too concerned. For the sake of conducting a test for independence, you just need to write this down. But if you're really keen on getting down and dirty, I would suggest watching the other 2 videos on the chi-squared distribution. You can check the video description. I'll put links up. But it gets a little bit interesting. Each of these singular joint frequencies are actually derived from what's called a multinomial distribution, and because the sample size is large enough, we can approximate it with the normal distribution. Woo! I can hear some people's minds exploding, but that's okay. Let's use this formula here, and we'll see if we can calculate at least this chi-squared statistic. So what happens is we take each of these 6 joint frequencies and we subtract the expected frequency, square it, and then divide by that expected frequency. So you can see we've got 15 minus 14.6 squared divided by 14.6. And then we do the next one, 30 minus 27.1 all squared divided by 27.1, etc., etc. And you can kind of see what's going to happen. The closer that the observed frequencies are to the expected frequencies, the smaller this chi-squared value is going to be. And the further away the observed frequencies are from the expected frequencies, the larger the chi-squared value is going to be. In this case, if you summed up all those 6 values, you'd get 2.84. All right, so let's see if this chi-squared statistic is large enough to reject our null hypothesis. Well, to answer that question, we're going to need a decision rule or a critical value of chi-squared. Now, for 2 degrees of freedom, the critical value is 5.99. Now, I haven't mentioned it yet, but we're using a 5% level of significance for this test. You could do it with other levels of significance, but 5% tends to be the done thing. Essentially, what that really means is that for this chi-squared statistic, we're happy to hold on to our null hypothesis so long as our chi-squared statistic doesn't push up into the most extreme 5% of the distribution. So if it pushes up into this yellow region up here for 2 degrees of freedom, then we're going to reject the null hypothesis. We're going to say, you know what? The chi-squared stat is too big now. These observed frequencies are now too far away from our expected frequencies to realistically hold on to our null hypothesis. And if that's the case, we'll reject the null. But how do we find out what this point is? Well, your Excel formula can help you. You can go equals chi-squared.inv, which provides for you a chi-squared value if you input a probability. Now, the probability I've put in here is 0.95 because it requires what is the area below this figure that you're seeking. And of course, it's going to be 95% or 0.95 because it's 5% above that particular value. And the 2 here represents the 2 degrees of freedom. And if you put that into Excel with that equals sign at the front, it should give you 5.99. Now, if you're using chi-squared tables, you can find it as well. It's pretty simple. You just make sure you look down for the 2 degrees of freedom and you roll across until you find it says area to the right of critical value. So of course it's going to be 0.05. So it's slightly different to the way Excel looks at it, this particular table. But you can see we get 5.991. So 5.99 is our guy. So our conclusion, therefore, is do not reject the null hypothesis, as the chi-squared calculated value is less than 5.99. It's only 2.84. So at the 5% level of significance, there's not enough evidence to suggest sex and social media preference are dependent. And I might even put it in there at the 5% level of significance, just to be nice and complete. Just be careful in your conclusion. You can't conclude in this case that the 2 variables are independent. All we can say is that there's not enough evidence to suggest that they are dependent. It's like a double negative. It's like saying that someone is not guilty of murder, for example. That's not to say that they're proven innocent. It's just that we don't have the evidence to show that they're guilty. And that is your chi-squared test for independence. Hopefully that's been useful to you and also illuminating in that it's just a goodness of fit test by another name, isn't it? We're testing whether this observed distribution fits the theoretical distribution that we can derive from independence. Interesting. Anyway, that will do us. My name's Justin Zeltzer. All my videos are up on zstatistics.com. If you like my videos, feel free to like and subscribe. Or you can send me an email. My contact details are up on the website. But other than that, I will see you around. Catch you later.